Good morning and welcome back. Good to see everybody. I have to tell you today, and I don't mean to say this lightly, today is a day that will change your life forever because of this class. We're going to get into Stan, and some of you will become Stan addicts. Well, maybe not, but in the last time I taught this, several of the students loved Stan so much that I think they created wallpaper on their house of Stan syntax and stuff. So, just so you know, today is a big day. Are you ready? Don't answer that. But first, let's start with some announcements. You're able to see my screen, I take it? Is that right? Perfect. So we have a formative assessment out again. Should have just been released at midnight last night for next week that covers stuff we did before. I will also note that homework 2 I'm not going to assign until next week. So I want to get you... homework 2 will be about using Stan to do analyses. So I'm going to talk about Stan a little bit more and get involved in that in homework for you to follow up with that. And it's also similarly timed because the last full week of the month, the week starting September 23rd, I will be unable to teach. I will be on a different continent at a conference. So I will not be teaching that week live. Not sure what to do with the content yet. I have an idea or two, but certainly homework, being able to do your homework during that time should work. Hopefully. I gotta stop hitting the desk. Put my hands up over here. My hands in my lap. So, as I mentioned at the beginning of class, today is going to change your life. I mean that. It's going to be amazing. Well, philosophically, one way or the other, your life will have changed in this one little bit of time that we have together today, just because, life, right? Evolution, something like that. But I do hope it changes it for better. We're going to talk about Markov chain Monte Carlo, which is a Bayesian estimation technique, and Stan, which is a program that does Markov chain Monte Carlo, among other estimation methods as well, too. The context for today is this. Remember, I mentioned at the very beginning of class, this is somewhat of a difficult class because I'm going to be throwing Bayesian at you, which I'm assuming you're in the class, so you may have a little knowledge of, but maybe not the full knowledge of, or where you feel comfortable with. And then I'm going to be throwing psychometric models at you. And again, you may be in a different trajectory with that. Everybody's got their own plan. Everybody's in their own pace. So to start, we're going to talk Bayes only, and we're going to stay away from psychometrics. In this lecture, which is actually a 3-part lecture, we'll talk about Bayes in the context of linear models, linear regression. We're going to start with very basic models, very empty models, and basically moving the idea from that die roll example that doesn't really look like a model, even though it was, into something that does look like some type of model that you're used to. Usually in your first class in graduate school, we get heavy into linear models. And the purpose for that, again, is to hope that you have enough sufficient training. We all have done regression analyses. We've all done analysis of variance before. So you've had sufficient training on the statistics side. I want to show you what Bayes looks like under that regime to begin with. And then, once we're done with Bayes, we'll move over to psychometric models, introduce those, and put Bayes with those as well, too, because there are a few more catches as well. So, let's dive in, shall we? Here we go. Today, we're going to talk about an introduction to Markov chain Monte Carlo. I will call it MCMC. So, if you hear MCMC, that's what it is. If you're in other fields, it might just be called Monte Carlo. And so I'll get to that in just a bit. We'll also talk a little bit about Stan, and we'll do both linear models. Again, this is a 3-part lecture. It's likely to take several class periods, but we'll find out. And again, please do stop me if you have questions or comments or anything that I can do to make this more clear. I cannot welcome them enough, and I treat each one of your questions with the respect it deserves. And I will also remind you, if you have a question, it's likely that some of your classmates do too. So you can do everybody a favor by asking it. Okay, on that note, I'm actively trying to not slap my desk. Really trying hard. I don't know why that's a tick of mine, but we're working on it. This right here, believe it or not, is the output of a Markov chain Monte Carlo algorithm. What does that look like to you? We'll do this. You see, my PhD is actually in psychology. I used that line before. I've got a PhD in psychology. What do you think about when you see this plot? Does that sound like psychology enough for you? Like a Rorschach type? Yeah, these are what we call time series. So this is two parameters of a model. A Markov chain, this sort of demonstrates what a Markov chain does. We literally try to sample values of these parameters from the posterior distribution. So hold off for a moment to understand what we think the posterior is, right? Because if we knew what the posterior distribution is, if it was so easy to sample from, why don't we just use it, right? Hold off for just a second. There's a little bit of a magic that happens for what the posterior happens to be in many cases. But a Markov chain algorithm tries to sample parameters from that posterior distribution and does so that in every iteration of the algorithm, each parameter has a chance to move or to change its value. The idea of a Markov process is sort of this stochastic process where a value might change, might move from different states, right? So at time 1, it's state A, and at time 2, it might be either state B or state A with certain probabilities, right? Sort of a random walk. The same thing happens in Bayesian Markov chain algorithms. Here we have beta 0, which turns out to be an intercept in an empty model, and sigma, which is the model, the residual standard deviation in this case. Each of those values from a very basic regression analysis, as we enter a Markov chain, in every iteration, each one will have a chance to change its value. And across thousands of iterations, here each of this is 10,000, this plot that you see right here, sometimes called a time series plot, more colloquially, and I can say that this morning, colloquially referred to as a caterpillar plot, because if it looks the way it's supposed to, it should look like a fuzzy caterpillar. Yeah, I'm a grown man. I said fuzzy caterpillar. That happens. So that plot right there is where the parameter was at each part of the chain. And you'll notice there's multiple colors on this, although they're overlaid on top of each other. You can't really see. But there was actually 4 chains run all at once. And so this is just a depiction of how the parameter moved across iterations throughout. And then if you were to flip this plot on its side, right now you have the caterpillar portion. If we were to go and turn it so that the y-axis was now our x-axis and make this into a histogram, you'd have the beginnings of what looks like a posterior distribution for each of these parameters. And that's basically the process of the Markov chain. It's magic. Almost all Markov chains work the same way. We allow all parameters to change states for every iteration. And if we follow that, if we build an algorithm that does that and has a few other features, it turns out through magic of mathematics, if we run this chain long enough, we pretty much were guaranteed to get convergence to a posterior distribution. So it's pretty cool. All right. So this, by the way, as I mentioned, so if you take this caterpillar plot, turn it on its side, and make a histogram of it, this is a smoothed version of the histogram. So there were 10,000 draws across 4 chains from that previous plot. So that's 40,000 sampled values of beta 0 and 40,000 sampled values of sigma. And so if we were to make a histogram and we were to smooth out the rough edges, make the bin width very tiny and smooth out the rough edges, this would be the shape of beta 0 posterior distribution, and this would be the shape of sigma's posterior distribution. This is the output from a Markov chain. We have posterior distributions. What do we do with them now? So the funny thing about it is Bayesian algorithms can be highly complex. The one in Stan is really cool. It uses some Hamiltonian dynamics from physics. Sounds really complicated and really cool, right? You can make everybody think you're smart when you talk about this type of stuff. You are smart. Don't get me wrong. But you can just show off a little bit. The bigger picture is you do all that, you get this distribution, and if you want to summarize your parameter, you're back to basic introductory statistics. How do we summarize pretty much a symmetric distribution? What's its measure of central tendency? The mean. So we take the mean of our posterior distribution, and we call it our parameter estimate. How do we summarize the variation in that posterior distribution? Spread. Basic statistics would tell you a standard deviation would be a good measure of it. And sure enough, that's the analogous quantity to our standard error in frequentist or non-Bayesian statistics. All right, now with skewed distributions like sigma right here, you'll note this is a little bit skewed. We would expect that for a finite sample with variance. a variance parameter, right? It has to be bounded below by 0. And the sampling distribution of this thing for finite samples kind of looks chi-square. Depends on what I put for a prior. I haven't talked all about that. But this is another case where the mean gets moved out because it's poled in the direction of the skew, right? This is positively skewed. So the mean would be actually moved up a little bit. So that's one thing to consider as you go forward as well, too, is that sometimes our summaries of Bayesian models are a little bit different than what we'd see in other non-Bayesian models. Let me get back to that in just a bit, though. All right. So Markov chain, Monte Carlo estimation, and Bayesian analysis. Really, our goal in Bayesian statistics is to estimate the posterior distribution. That's our goal. We want to get to the posterior distribution. Up to now, actually from lecture 1, where we described the probability, modeling the probability of rolling a 1 on the die roll, we've worked with these posterior distributions that were, I would call, well-known, or better yet, well-defined. Right? We could tell, using some mathematics, some algebra, and some pattern recognition, that a binomial data model combined with a beta prior distribution on the probability parameter would result in a beta distribution for the posterior distribution. We could show that, derive it. But that's one narrow case. In general, I would actually step a little bit further. If you use likelihood distributions from exponential family models, which if you've never heard that term, it's hard to define. A lot of the statistical models we use come from this exponential family of distributions. That family of distributions sort of has a form to it that allows for prior distributions to be conjugate. So remember the term conjugate prior, the prior distribution and the posterior distribution are the same. But quickly we move away from that setup. Most of the time, posterior distributions are not easily obtainable. Right? We have no idea what the distribution happens to be. Actually, I have a question. Let me go back. There was 4 chains represented here. Each chain is a different simulation. That's correct. So the idea being that in a Markov chain, this Markov process, there are times where this Markov chain may sample itself into basically what we need to ensure is that the sampling process, this process of moving from wherever to the center of a posterior distribution sampling, is consistent. Basically, we don't end up in a segment of a posterior distribution that's not really an optimal one, not a good one in a likelihood sense. So we end up starting Markov chains 4 different times, 4 different simulations with different starting values, and to see where they end up. Hope that answers the question. Yes, I see another question. Mm-hmm. That's a great question. The question is, how does a parameter's value get changed? Is it random? Is it something specific? Great question. Turns out it is a random process, and the algorithm itself defines the probability of changing. But it's complicated, and I'll work on the complication as we get through the lecture today. So basically the idea is this, there's several different types of Bayesian algorithms. Up to this point, we talked about conjugate priors. So you have a well-known distribution at the end. That well-known distribution, if you have that, Gibbs sampling is literally just drawing from it. So our beta binomial example, we could have just used the beta distribution with its known parameters and sampled from it to build our posterior. When we're not in a conjugate prior, that becomes difficult. But the Markov chain algorithm that's most commonly used is something called Metropolis-Hastings. Metropolis-Hastings involves an additional step, which is the proposal distribution. So basically you have a distribution that allows you to draw at random a parameter value. That random parameter value you can then evaluate with your model data likelihood, your prior, and your proposal distribution. So each of those has a likelihood involved in it. And Metropolis, this is an algorithm, believe it or not, dates to 1950, which is pretty cool because we didn't even have computers that were wide scale back then. They then would go and create the probability of switching the state of the parameter as a ratio of those Bayesian likelihoods. So likelihood of the model data of your new parameter versus your old parameter times the ratio of the likelihood of your prior distribution for the new parameter times the likelihood of the prior distribution from your old, plus the likelihood, depending on what your proposal distributions are, basically canceling out how likely it was to sample in that spot to begin with. So all of that is really, really complicated, but it works, and it works spectacularly. So the answer, the long-winded answer to your question is, it's all random, but not random as if we have a uniform distribution of the parameter. It's maybe, it may be a, sorry, I'm laughing at my thumb icon on my screen. It may be the case that that random process it basically will follow this distribution eventually. Does that answer your question? Thank you. All right. So most of the time I mentioned our posterior distribution is not obtainable, so we can't really use the properties of this posterior distribution to estimate parameters. I mentioned in my answer just a moment ago, if we know the posterior distribution itself, we know it's going to be a beta, and the alpha parameter is this, and the beta parameter is that. We just draw from that beta distribution. It's sort of uninteresting. But when we don't know what it is, we have a complicated process to use. So, as you know, in other versions of statistics, we can use what I would call an optimization algorithm. Something where we want to find a maximum value of a posterior distribution, right? So we could define a posterior distribution, and then we can go use Newton-Raphson to calculate its peak, right? Basically, we have Bayes' theorem for likelihoods, and we use that. That's our posterior distribution. We put that in a Newton-Raphson, like in R, the base R has a function called optim. Optim will try to figure out the peak or the minimum or the maximum of a function numerically. We could use that. So I will note that in Bayesian estimation, although most of our class is about Markov chain Monte Carlo, you can still estimate Bayesian parameters without it. But it becomes increasingly difficult when the model gets more complex. I want to mention this to you because oftentimes you will see practitioners say Bayesian is Markov chain Monte Carlo. I've even had reviewers as an editor argue that, oh no, there is no such thing as Bayesian if there's an MCMC. I'm like, hold on just a second here. You can do Bayesian algorithms without MCMC. Most of our class, but those, actually, let me back up. Those are usually either very narrowly defined, not general, or very difficult to estimate. And as your model gets increasingly complex, it may become increasingly difficult to get a stable result from it. So just to note that. There we go. There's another method out there called variational Bayes, which is a fairly, relatively speaking, new method, which approximates the center of the posterior distribution using this variational distribution effectively to try to figure out that center. This is a fast method to try to figure out the center, but it doesn't necessarily do a good job at approximating the rest of the shape of the posterior distribution. So in some cases, this is important. Like if you really want that point estimate but don't care about the noise to it, variational Bayes may be good for you. And when I mentioned that, there are places all the time. I think a lot of our, dare I say, our large language models, a lot of our machine learning techniques end up wanting that center point and couldn't care less about more of the distribution around it. So there are cases where you'll see it. But I just want to make the point before we get into MCMC, because I'm never going to talk about these methods in this class. I'm only going to talk about MCMC for the rest of the class. Just remember, on September 10th, 2024, my goodness, September 10th, 2024, I told you MCMC is not, Bayesian is not just MCMC, okay? Cool. The other thing I will tell you is Bayesian is not just MCMC, but all MCMC algorithms are Bayesian. How about that? Okay, last bit. MCMC, what we talked about, what we're talking about, the basis for the rest of the class, functions by saying the following. Basically, I don't know what the posterior distribution looks like. I don't have a picture of it. I don't have a known form for it. In fact, it may not even follow an easily defined model, distributional family. However, I'm going to try to draw its shape. And I think of this Markov chain picture right here as doing just that. This is sort of etching the values of the Markov chain, right? Whenever you grab, look at this, these first values that are close to the center here, like 170, it's like, oh, I'm going to just fill up the shape of this distribution. Every time I draw values, if you could visualize the histogram of the Markov chain for every sampled value, it'd look very rough to begin with. And as you get more and more and more of them, it starts to build its shape. And then at the end, it looks like this. So MCMC approximates the posterior distribution through a sampling process itself. Right there. So it's a sampling algorithm, right? There it is. How are we doing so far? Questions? Please do. Yeah, good question. The question was, is draw from the same thing as sampling from? And the answer is yes. I apologize for my statistics colloquialism. That itself, when I say draw from, really means sample from, and I should be a little bit more precise in my language. Yes, every value, when I say we're drawing from the posterior, we're sampling random values from the posterior distribution to build a shape for it. Good question. Thank you for letting me clarify. Other questions? All right. So MCMC algorithms iteratively sample from the posterior distribution. So the word iteratively is the point of this bullet right here. What that means is, I mentioned every iteration, every parameter has to have a chance to change its value, right? Actually, let me address this one question real quick. Why is it hard to shape the posterior distribution? So it turns out, in most cases for data, we don't know what it looks like. The case that we had previously, the beta binomial distribution, we knew the beta distribution looked like beta. And in fact, we knew its two parameters because we could talk about how they were updated once we rolled the die, right? We'd add 1 to alpha or we'd add 1 to beta depending on what the result of the die roll was. But think of it this way. If I didn't have that, if my data were normal, which is what this model is, and I used let's say, I'm going to pick a value out of my head, pick a what's your favorite distribution no one's ever heard of? I don't know, Cauchy or inverse gamma or something along those lines. Once we combine that with the model data likelihood, there's no tractable or easily definable form for what the posterior distribution should look like. We don't know which family it comes from. And that goes to another thought. Think of it this way. If you look up distributions in statistics, let's see here. Like we go to Wikipedia and we talk about probability distributions, you'll note a ton of different values here. Bernoulli, binomial, exponential, normal, Pareto, all these have terms to it. If you can tell me a distribution has this term, we can figure out its shape mostly. However, a lot of combinations of model data likelihood and prior likelihood don't result in a distribution with this family, a name. Think of it this way. Just because in statistics, we have a family of distributions that have a name to it, that doesn't mean that any other distribution of data has to follow them, right? We use these families of distributions to talk about certain statistical phenomena that we're familiar with, but data come in all shapes and sizes and forms. So it's not the case that these are the only set of distributions in the world. A distribution can be anything. So we don't know what a posterior distribution looks like because one, we may not know which shape it has, which family it comes from. But two, even if we know its family, we may not know what its parameters are. For instance, I'm going to tell you right now, a lot of what we're going to do in like confirmatory factor analysis, we'll know the posterior distribution will be normal for a lot of our parameters. But just because we know it's normal doesn't mean we know what its mean or its variance is. So we have to sort of sketch the posterior distribution to figure out those parameters. Does that answer your question, Ryan? Thank you. Okay, so going back here, so iteratively refers to the feature that in the picture I had before, this was a simple linear regression with no predictors, what we call an empty model. We have a mean, beta 0, which is really the mean of our data. We have a standard deviation sigma squared. Iteratively means we don't necessarily have to sample beta 0 and sigma squared simultaneously. We just have to allow them to change their value within one iteration. So it could be the case that we sample beta 0 separate from sigma squared, right? So in iteration 1, we sample beta 0, we sample sigma. We go to iteration 2, we sample beta 0, we sample sigma. That's the iterative process. It iterates, it changes, and values change based on what happens. So for fairly simplistic models, each iteration has independent samples, but most models have some layers of dependency included, right? Which can slow things down. So what do I mean by that, right? If you think of, again, this plot right here, right? So in a linear model, and again, beta 0, you can think of this as the mean of a sample of data, and sigma is its standard deviation. When it's an empty model, basically the mean, beta 0 should be the mean of the data, and sigma should be the standard deviation. But there's a dependency between the two, right? You can what is a feature of the standard deviation? If you go back to basic stat, and I tell people don't memorize formula, but I'm going to remember a formula real quick here. In the standard deviation, under the square root, there's the sum of each observation minus what? Minus its sample mean, right? So in a Bayesian algorithm, the sample mean in this case is sampled. So if you think about an iteration, let's look at this dark blue line. Look where my arrow is at the top of it. It's very high compared to where the center of the distribution is. This might be the largest value sampled in the posterior, right? It's 210. Well, if you put a sample mean of 210 in your standard deviation formula, what's going to happen to your standard deviation if it should have been 170? Right? It's going to look like there's more error to it. Right? So the parameters together, what I'm trying to say is the parameters are yoked in ways, even in basic models, where one will depend on the value of the other. Right? We're used to frequentist statistics saying, hey, the standard deviation is the amount of variability, but the center of that is the mean. But in our case, from a Bayesian perspective, the mean is just another parameter, and we don't know what happens to be. So rather than putting the mean into our best guess, our sample maximum likelihood estimate of the mean into the sigma formula, instead our likelihood is going to have to involve it being variable. And that dependency that you see there, that one parameter depends on the other, is part of the iterative nature. It's part of what the Bayesian algorithm does well with, which is it doesn't necessarily make you think, hey, that standard deviation needs a fixed mean. In fact, that fixed mean may have some variability to it as well. How am I doing with that? It's an interesting concept if you're used to just basic statistics, where the mean goes in the standard deviation formula, but that assumes you know the mean with certainty. So you can guess what's going to happen to the standard deviation in the Bayesian sense. If you were to compare this model result with what you got from frequentist estimates, you would end up seeing, most likely, that sample standard deviation is probably going to have a wider standard error to it, and it may even have a different center point to it compared to what you have before, based on not having certainty about the mean parameter. So what I mean by that is these are the layers of dependency that happen in Bayesian statistics, where the iterative nature of the algorithm starts to try to unpack which parameter depends on which. And we're uncertain about both, right? And if you think about it, this Bayesian algorithm, we're going to start with a random starting point, probably nowhere near the middle of our Markov chain. It's posterior distribution. And we're going to end up getting to a central place where we don't know either, but that lack of understanding of either is going to be reflected in our posterior, the width of our posterior distributions. All right, how am I doing with this? Does this make sense as a concept? This is a very different idea than what happens in frequentist statistics. Right? In frequentist statistics, you get your maximum likelihood, you get your point estimate. If you have another parameter that depends on it, you put it in the process, it's done. In Bayes, the things that you don't know are allowed to have error, which can be a very good thing, I think. You're not ignoring it as you go forward. All right, back to the slides. There are numerous variations of MCMC algorithms. They use two types of sampling generally. The direct sampling, as I mentioned in the answer to a question previously, is called Gibbs sampling. And it's usually used when you have conjugate priors. And then there are indirect sampling. We call this rejection sampling sometimes, where we will propose a parameter value and either accept it or reject it with some probability that is a combination of model data likelihood, prior likelihoods, and proposal densities as well too. Turns out the term for that is Metropolis Hastings. Stan uses an algorithm they call Hamiltonian Monte Carlo. The Hamiltonian creates better proposal values. So it's an efficient version of a Metropolis Hastings algorithm, but we'll talk more about that as we go further. Actually, we'll talk more about it now. Efficiency is the main reason why we have so many algorithms. What do I mean by efficiency? An efficient algorithm is one that samples the posterior distribution in a short number of iterations. Right? You can think of it this way. If we are proposing new values of our beta parameters, and we only accept those that are close to the center of our posterior distribution, we could make a really inefficient process if we had, let's say, a uniform proposal distribution. We just allowed parameters to be drawn from, let's say, negative 100,000 to positive 100,000, especially if this previous example, I'll put numbers to it. We knew our mean parameter was like 170. But if we draw values between negative 100,000 and positive 100,000, we're only going to accept those that are closer to the mean, right? Between 100 and 200 or 100 and 300, something like that. But think of that uniform process. You could even quantify how likely it is to draw something between 100 and 300 if the whole range goes from negative 100,000 to positive 100,000, right? It's tiny, tiny probability. So you'd have to run that algorithm a long time to get the values for it to switch to in close to where it goes. That is what we call an inefficient algorithm. We'd rather have efficient algorithms. So again, efficiency is how quickly the algorithm converges and provides an adequate coverage of the posterior distribution. When I say adequate coverage, we want that posterior density to be fairly smooth. Right? If you don't sample long enough, you've all seen histograms before, right? Histograms of small samples of data can be very irregular, very jagged, right? We want the sketch to look really nice and smooth, right? Almost like art. In fact, I'll give you extra credit if you put a picture of a posterior distribution as artwork in your house. What about that? I think that could make for some pretty art, don't you think? Is anybody willing to try that? Wait till after this lecture, you might be willing. But that being said, I will say this. The problem about picking algorithms is that no algorithm is uniformly most efficient for all models, right? Some are better than others depending on the context of model. But that's why software packages like Stan or JAGS, even M+, don't make you choose which algorithm to use. Although Stan just defaults to Hamiltonian. JAGS actually has quite a few algorithms, although JAGS, remember, is short for just another Gibbs sampler. And remember, I just said Gibbs is direct sampling from the posterior. Right. The bad news, though, to this is that with a general algorithm like that, your model may take a large amount of time to reach convergence. Now, depending on which type of model you're using, that might just be hours. But I'm not going to kid you. I've run models that have taken days. I've run models that have taken weeks. And at least one of you knows what I'm talking about with diagnostic models and using M+, although not using Bayes. But there are models that take a long time. We're not going to cover most of those in this class. But I think most of the things we'll find in this class will converge fairly quickly, certainly within minutes, maybe up to an hour. So the other thing you can do if you really want to is you can code your own custom algorithm to make things run smoother. And what I mean by that is you can, if you know the ins and outs of Bayes, you can build your own algorithm. There are times in research I'll have to do this myself just to make things work a little bit more quickly with things. But I don't know that you want to do that. Most of you want to do that. It generally, like for me, like I don't work on cars, but this is my car. Like I like putting the pieces under the hood. You know, there are people, the car guys or the car people that, oh yeah, I'm gonna go and swap out the brakes this weekend, or I gotta go and put a new engine in, whatever. to me, that's Bayesian algorithm building. I enjoy doing that. For you, I don't think I'm going to give you those skills. But in research, if you want to learn those skills, there's certainly a project or two I'd be happy to work with you on, but not in this class, not for this class. All right, questions? I'm doing my best to not hit the desk. We'll see how it works. Yes, Vladimir. In this case, in our little simple example, absolutely. They're both really important, right? So think of it this way. Let me see if I can switch over and do some drawing here. All right. So I'm going a little bit further in. Oh, geez, I just ruined it, didn't I? Let's see if I can restore it. Come on, you can do it. Shame on me for removing my iPad. There it goes. There we go. All right. So beta 0. Let's think of it this way. The model itself was this. Y equals beta 0 plus beta 1. Oh, no, there's no beta 1. What am I talking about? Plus error. And error follows a normal distribution with a variance sigma squared. Okay? So what this implies is that Y follows a normal distribution with beta 0 and sigma squared as its parameters. That's basically what this is implying. This is the model data likelihood itself. Let's put it that way, right? And if you remember the normal distribution, f of y, this case, would be equal to 1 over the square root of 2 pi sigma squared of exp of negative, this would be y minus beta 0 squared over 2 sigma squared. Okay, so this is our model data likelihood. So far, so good. Guess what's going to happen if sigma squared is very large? When you go and sample beta 0, right? Beta 0 itself right here, the distance from your sampled value in beta 0 from every observation drives this part. But how much that gets weighted is based on sigma squared. Right, so I think your question was, how do these two depend on each other, right? Is that right? Right? So what I'm trying to say is, because they both show up in our model data likelihood, having a very extreme value of 1 will impact the likelihood of the other in that iteration. Right? If we put a very large beta 0 in here, that means sigma squared is probably going to be higher than it wants to be. Its model data likelihood will be higher on the high end of it, and vice versa. If we put a very large sigma squared in here, then the density for beta 0 will be much more uncertain. It'll be much flatter at every different point. And so because both parameters show up in the same function that we use, this right here is the f of y given our parameters, right? In our Bayesian algorithm, actually here, the posterior distribution of beta 0 and sigma squared is proportional to, this is our model data likelihood right here, and then we have a prior likelihood of beta 0 and a prior likelihood of sigma squared. So because what I'm trying to say is this likelihood, the value that comes from it, will depend on the value of each of those beta 0 and sigma squared. Within one iteration, if one of them changes to be an extreme value, the other one's going to have an impact to it. Right? It's just over the long run, we want to see how both work together, and we eventually achieve convergence. Does that answer your question? Are my answers too long-winded? I feel like I'm being too nuanced here. Hmm? Yes. That's right. If we have more model parameters, they're going to show up in this equation. That's correct, yes. You're welcome. Other questions? All right. Moving forward. We were commonalities. I believe we were right here. Yep, there we go. So what are some of the commonalities across Bayesian algorithms? Despite having fairly broad differences, I mentioned this way they sample values from the posterior. There's quite a few things that are similar. So for instance, there is a period of a Markov chain where sampling is not directly happening, is not directly from the center of the posterior. I should really say center here. So what am I talking about here? In a Markov chain algorithm, because I mentioned every parameter has to have a chance to change its value in every iteration, let's go back to the beginning of the algorithm. How do we get started? Well, it turns out we gave a random value to each parameter in our model to start with. And that random value likely has nothing to do with where they're going to end up. In fact, if you read the Stan technical manual, I believe Stan starts its parameters between -2 and 2. All right? You saw the Markov chain for beta 0. Its center was at 170. So when we start at -2 and we move all the way to 170, there's a number of iterations that are involved that are effectively the parameters walking this path, literally random walk, that eventually move them toward the center of the posterior distribution. And what I showed you with the caterpillar or time series plot to begin with, that flat line right there is the tail part of our sampling process. The beginning part was omitted from it. So this period, there is a period of each Markov chain that we do not include when we summarize the Markov chain. That period is sometimes called a burn-in or a warm-up, and sometimes other times called tuning, depending on the algorithm you use. But the idea of the Markov chain is that if you start at any random value, so long as those values are within the parameter space, like values parameters can be, not negative values for variances, for instance, but values the parameters can be, any random value, mathematically, so long as our data behave the way we expect them to, and so long as we allow every parameter to move at every iteration with proper distributions for priors and proposals and so forth, we're guaranteed in the long run, if we sample this chain long enough, we'll eventually get to convergence. And convergence is when that parameter moves toward the center of the posterior distribution. So the burn-in or warm-up period is the part of the algorithm we omit when the parameter is effectively en route to where it needs to go. The question in the chat is, how do you know when the burn-in period is over and what indicates that? I'll tell you what indicates it, and I'll then tell you, you never fully know. I just told you the answer. What indicates it is the time series plot. So if I go back again to our first picture here, this parameter, what you see in this plot is a parameter that's, while has definitely variation, it's not moving wildly in a direction. There's no direction to it, right? It's flat. Flat and wide is what you want to see with time series plots. That indicates that your parameters are in the center of the posterior distribution, right? Just remember this posterior distribution. These are pretty good sketches of it. And so if beta 0 started at -2, eventually it's going to have to wiggle its way to the middle of the center of this posterior distribution. And once it gets to the center of posterior distribution, because the model data likelihood is concentrated here, it will have an infinitesimally small likelihood of moving back to -2. In fact, it will probably never get back there. So once it gets close to the center, it's almost like the center of the posterior distribution is a black hole. It can never escape it, right? And the parameter itself is pulled into the gravity of that center of the posterior distribution. So our idea for when a burn-in is over is when we see what we call stationarity, a parameter that's certainly variable but no trend to it. Now, how do we know when that happens? We do not prior to running the Markov chain. So what we end up doing is we have to check at the end of the Markov chain whether we achieved convergence. And that is a process that I'll show in a few slides and maybe be the next time as well too. But I will say the easiest version of convergence is I believe we call it the ocular whatever. Anyway, the eye test. I don't know if I've wasted my discussion talking about physics and stuff. Whatever funny, not funny stat humor I can give. Here's the thought. take a look at you can always plot your time series of your parameters, and if they look fairly flat, like there's no trend, variance is good, trend is not, that would indicate you're fine. In practice, not knowing this ahead of time, what you end up doing is trial and error. So you set each algorithm will ask you how many iterations do you want for burn-in. In Stan, they call it warm-up itself. And you run it for that many, and if for whatever reason it didn't converge, you increase that number. Right? So it's just a trial and error, unfortunately, trial and error for how it happens. But it's basically sim model here. So sometimes the simulation doesn't quite work. The other part of that, and I just mentioned it here, is another commonality across MCMC algorithms is that methods that we use to assess convergence are mostly similar as well too. So it doesn't have to be that the Gibbs sampling algorithm, we use one method for convergence, and we have Metropolis-Hastings algorithm, we use another method to assess its convergence. We still use the same methods here. This assessment of convergence is done sometimes using the plot, sometimes using some statistics, which we'll define in just a bit. But in almost all cases, there's a need to run multiple versions of the Markov chain to assess that the posterior is in the same spot. What I'm showing you today, and for most of class, are posterior distributions that should have one mode to them. One mode meaning one peak, meaning that parameters are going to be drawn into that mode as they go. But there are cases, particularly with certain prior distributions, where you may have more than one mode for your posterior. And those are hard to sample from because, again, once a parameter gets close to the center of a mass of a distribution, it will not escape it because that likelihood is so, it would take almost like an infinite number of draws to have a chance for it to move out. So when you start multiple chains, you're checking to see if you're ending up in different modes of a posterior distribution. And that would be indicated by flat time series, but not overlapping. You know, that first picture I showed you had 4 chains and you couldn't differentiate them. That's how well mixed. That's how we were very certain they were in the same mode of a posterior. If we have multiple modes, we'll have time series that are not overlapping. And you'll be like, wait a minute, this is not converged either. So another way of looking as well. And then finally, once we have a converged algorithm, once we got everything working, how we summarize our analyses is also the same across algorithms. Right? Typically, we use summaries that involve sample statistics, mean, median, mode, confidence intervals, areas, quartiles. These are areas that we talk about underneath the curve. Area under the curve, quartiles, proportions in the center, all those are the same. In fact, what ends up happening is once you start doing this more frequently, nobody will talk about which algorithm you used, and they'll just look at your results. So I'm throwing a lot of definitions and words at you. This is almost like a very difficult class in that I'm throwing all these terms at you without actually well defining them yet, as we're going to get there. But that's one of the things that you can hold on to, is that despite the fact that we're talking about these multiple algorithms, they'll still have the same features. A burn-in period, how to assess convergence, how to summarize the parameters. There are some, if you're in a rejection-based algorithms, that's Metropolis-Hastings, Hamiltonian Monte Carlo, those are usually called that. They have a series of, another period of that Markov chain where they try to tune the proposal distribution. It's like a burn-in as well, too. All right, questions? We got 10 minutes. I got this. Maybe I don't. Yeah, I do. You want confidence in your professor, right? Confidence. I'm confident in MCMC. All right, let's talk about it. Let's give a demonstration real quick here. We're going to use a model for a normal distribution. We're going to demonstrate each type of algorithm with this real quick. We'll investigate each of these algorithms briefly, and then we'll switch over to Stan and show the syntax for it as well. And then we're going to end this lecture by talking about how to assess convergence, and how to report parameter estimates. So here, I'm using an example data set that I swore I've used probably since I was an assistant professor, which was a long time ago. This is clearly simulated data. It's height and weights of people who are on a diet intervention group, which, believe me, I definitely need in my current state. You can find the data online and the story for them online. There's a file in our shared folder called dietdata.csv. I'm sorry, our GitHub repo, dietdata.csv, which is the data that I just clicked on right there. There's 30 people who participated in a study regarding the effectiveness of 3 types of diets on weight loss. It turns out this is only a cross-sectional study, so not great for looking at weight loss over time. And for those of you who take Lisa Hoffman's longitudinal class, you'd be like, what? You can't really study this cross-sectionally. I know. This is just to get us to talk about data with 30 observations. Okay? And once you see the results of this, you're going to be like, yeah, totally fake data. Totally fake data. But we'll see. All right, here's the variables in the data set. We got our ID number. We have a diet group, which is 1, 2, or 3. And I believe in this link, it tells you what they are. No, diet 1, diet 2, diet 3. There used to be a different story, I swear, where one was like a vegetarian diet, one was like a little bit like more of the keto, and one was like omnivore or something like that. I like the word omnivore. Why not, right? We're omnivores, except for vegetarians. Height in inches is the person's height in inches. Weight in pounds is the weight in pounds. It's a person's mass, weight in pounds. And the research question was this: are there differences in final weights between the 3 groups? And if so, what are the nature of those differences? So let's look at the data first. Ooh, look at that data. Does that look like any distribution you're used to seeing? All right, here's our height variable, weight variable, height variable. By the way, this is going to be our dependent variable. We're going to be predicting weight. Do you see any cause for concern in predicting weight with a linear model by looking at these data? Ask this quick question. This is me addressing your stat knowledge. It is bimodal. And Sergio, you meant approximately normal. You mean within each part of it. Is that what you're talking about? I will call that a mixture of normals is what I'd call it. If you want. Again, I'm just nitpicking. I'm sorry. I don't know how you put up with me. All right. But yes, bimodal. Both of those sides are approximately normal. What have you heard in your old stat classes? Should we be worried about this with data? By the way, I'm dwelling on this because to do Bayesian, you got to specify the whole model. And to specify the model data likelihood, you really got to understand that model pretty well. If I gave you this data in regression class, whatever that class was for you, would you have to do anything to it, like transform it? So I was going to agree with you up until that last part. But I'll say this, distinguishing 2 groups. Let's back up for a second. Imagine these were groups based on one of our collected variables, such as the diet group a person's assigned to, right? In a linear model, if that's one of the predictors, then that should center anybody in that group's predicted value to it. The bigger picture I was trying to get at, and Sergio, again, not picking on you, pretty close to what I was looking for there, is this. I don't know, maybe now I'm realizing I got to be a nicer guy to you, Sergio. I'm sorry. I got to do better. All right? Accept my apology, please. I'm sorry. I realize I'm just nitpicking. The bigger picture is this. In a linear model, this is our outcome. This is y. And we don't make the assumption that y is normal in a linear model. We say that error is normal. So that means once we predicted y with all of our other predictors and coefficients, what's left over is normal. So I say that because there's a common misconception and in some textbooks it's even reinforced. If your data aren't normal or are bimodal, you've got to do something to smooth the data out. And I would argue that it depends on your model. That depends on a model that insists that they be normal. And getting back to why I'm asking that for this class is our linear regression model technically is conditionally normal, meaning the mean of the data will depend on the parameters and the groups that we're predicting with, not the data itself. So just a heads up. Here's our height variable. By the way, usually a regression model makes no assumption about it. So once you look at X in a regression model, X has no assumptions, just that we observed it. We might assume that it has some variation to it. It's hard to work with a constant X. It's not really an X at all. It becomes part of the intercept. And then here is our weight variable by group. And this makes that normal distribution look a little bit better, right? There we go. That's what we were talking about. And here's 3 different regression lines put to the different groups as well. By the way, not a lot of error within group, but you can see what we're talking about there. So I sort of already hinted at what analysis is most appropriate. We're going to use a linear model, linear regression, actually. Some version of linear model. I say linear model because we used to just teach regression, and then we used to teach ANOVA. We sort of do that still, but then we put them together and we get ANCOVA. But ANCOVA, in the original days of ANCOVA, we didn't have an interaction between continuous and categorical trait. It's all together. That's why I call it linear models in a big umbrella. So the most type of appropriate analysis to me is a linear model where we're predicting weight as a function of the group a person was in for the diet and sorry, the group they were in for diet and their height, and potentially a group by diet by height interaction as well too, right? And the dependent variable is appropriate because it is not because it is multimodal, and not because like a mixture of normals or whatever we want to call it. It's appropriate because we have to think of the range of what we think that y should be. And in a linear model, y should be normal, or in this case, conditionally normal. But thinking about it, to me, the bigger picture is the question of normal involves having y be continuous. And while each observed weight is a bit discrete, there's enough variation in those observations of how many pounds each person happens to weigh that we could probably assume a normal will approximate it well. I didn't notice there was a question in chat. Sorry about that. You'd have to use a generalized approach here, Gaussian, right? So the idea that I was trying to get at, I think the question came when I was talking about whether the shape of the data were normal or not. In this case, it's more the idea of the model, right? The model is not assuming y is normal. It's actually assuming e is normal or y is normal conditional on once we predict what observation happens to be. So we could even play with the data in R here because Lisa Hoffman I know quite well. I have been drilled to center my parameters. Those of you smiling know Lisa very well too. It's kind of like some people treat flossing their teeth, like centering parameters for me. I'll just be real. Sometimes I center, sometimes I don't. If I need to describe something to Lisa, though, it better be centered. So if I have to ask Lisa a question and it's not centered, no answer, right? So just remember that. Now, for that record, I do floss my teeth every day. I actually have a water pick. It's wonderful. So don't worry about that. Okay. But the bigger picture is in terms of centering. Play games with that. The full model here, actually, we used an empty model to begin with because we're going to start empty, like Lisa likes to do. I actually like this approach quite a bit. It's kind of a dumb model, right? The estimate is 171 for our intercept. That happens to be the mean. And you can barely see it on my slide, but the residual standard error of 49.52 happens to be the standard deviation. So when you estimate an empty model, you are assuming y is normal because it's not conditional on anything, but the overall mean is 171, and we can tell right now 171 is in no person land right here, right? So it doesn't look like anything of what's happening. It's unlikely that that mean is a good summary for any of the data itself. But this gets into a whole bunch of things that you probably heard about a little bit in regression class or linear model class. Regression diagnostics, linear model diagnostics, error convergence, and stuff like that. And at that point, I think R is trying to tell me something. Connection refused. Turns out, I'm going to leave it here. We're going to pick up next time with this example. Does anybody have any questions for me before we leave off? Because we have less than a minute left. 15 seconds. 15-second question. Never say I'm not precise. It's fun when I teach online because I have a second hand. I can tell when that actually lit on network time. All right, everybody. Great to see you this morning. Hope to see you Thursday. If you have any questions or thoughts between now and then, don't hesitate to reach out. And I remember Vladimir has office hours at 9 tomorrow. I have it 10 to noon. And Vladimir also has office hours at 12 if you have those questions. So have a great rest of your day. Nice to see you. Thanks for coming.